So hello everyone. So let's start the second talk by Professor Raskin from Yale University. The title of his talk is Recent Progress in Geometric Langlands.
Thank you so much for inviting me to be here. This is really a pleasure. I never thought I would get to give a math talk with a view of the Great Wall. So yeah. So the first thing I want to say is that I know that this is a general audience. This is a quite technical subject. And so I have set up this talk accordingly. It's really meant to give people who aren't in the field I tried to give people a sense of what the subject is about. Maybe I was successful, maybe not. We'll find out. And so that's just to say that, for close friends who I see at many conferences on geometric Langlands or something, this talk really is not geared to you. Just a warning there. Okay, so I'm going to talk about. So over the course of the talk, we'll talk about sort of the abelian version of the story. Oh, it doesn't go on the screen. Okay. I'll talk about some of the non-abelian setup, and then I'll talk about what the geometric Langlands conjecture says. So kind of what I was just saying, so this is it's a technical subject, so I'm not going to be able to go into a ton of depth, but that's not my goal. So the main theorem of today's talk is called the geometric Langlands conjecture. So this is a result that was proved in a series of joint works with many people. So Dima Arinkin, Dario Beraldo, Justin Campbell, Lin Chen, who's here, Joachim Faergeman, Dennis Gaitsgory, Kevin Lin, and Nick Rozenblyum. And I'm not going to be a stickler about attributions going forward. That's kind of my once and for all. The big stuff is them. Okay, let's see. Thank you. Okay, so just to talk a little bit about the setup. So just before we start, we fix the field. I call it little k. It has characteristic 0, and you can take the field to be the complex numbers. That's fine with me. I just call it k, and it's easier for me in LaTeX. So a quick reminder is that an algebraic curve, it's something which should be a curve, and it's algebraic, so it's locally modeled on solutions to polynomial equations. So for example, if you talk about the set of all xy, where y squared equals x cubed plus 1, this is a great affine algebraic curve. In fact, it's a smooth one. So we can speak about many qualities and many topological qualities in algebraic geometry. So we can talk about connectedness, properness, which is a kind of compactness, and so on for these algebraic curves. So suitably understood, for the complex numbers, this theory of smooth, proper algebraic curves, that's my favorite setting, is going to be the same as that of compact Riemann surfaces, so you can think of those terms if you want. So I'm going to fix once and for all today a smooth projective curve x defined over my field k. So just a quick picture. This is x. Okay, so I'm going to fix a. So I want to just start by reminding I said I would do the abelian theory, and so this is kind of the story of divisors and line bundles, and I'll just give a quick reminder how some things work. So if I have a point in my curve, there's a corresponding line bundle called O of x. So these are functions, the sections are functions with a pole of order 1 at x. If I have a divisor, there's also O of d, divisor d, which is just tensor product indexed by, well, it's the line bundle where sections are functions with poles bounded by d. And I can twist line bundles by divisors in this way. Again, it's the same thing. I take sections to be sections of L that have maybe possibly poles bounded by order d. And then just a reminder, any line bundle actually can be written as O of d. And so then you can sort of imagine that you move from one line bundle to another line bundle by a series of kind of local modifications. So I start with my L, and then I kind of twist it to order n1 at some point x1, and then order n2 at x2, until finally I get to, I've twisted at all of my points, and that will get me my line bundle L prime. And so this is a little bit the picture you're supposed to have. Anytime you have two line bundles, you move by this series of modifications at individual points. So these are what we would call abelian Hecke modifications. So just abelian because these are line bundles, and Hecke modifications because I sort of changed the bundle only at one point. And this is something won't kind of explicitly occur, but this is the nature of Hecke modifications in the story. Okay, so in the theory of Riemann surfaces or algebraic curves, there's an important role that's played by various reciprocity laws. So just to give a quick reminder, if you have any meromorphic function, then the degree of its divisor is equal to 0, which is the same as saying that whenever O of D is isomorphic to O of D prime, the two divisors have the same degree. And then also whenever you have a meromorphic one form, the sum of its non-zero, both cases, it's the sum of its residues at various points is equal to 0. So these are called reciprocity laws because you have this sort of local information. It just happens around points, like the residue or the degree of the divisor. That's something which happens just right near some point x. But then when you're on this projective curve, the values you obtained at the different points sort of conspire to give you something like 0. So this kind of conspiracy is called a reciprocity law in the subject. So overall, the goal for today is to discuss non-abelian reciprocity laws on curves. So that's the setting of geometric Langlands for non-abelian groups. But the formulation of the main theorem, it's a little bit subtle. So if you just stare at these two theorems and then try to generalize it to GL2, that's not probably going to be so successful. At least you won't arrive at the theorem that I'm going to prove at the end. So I first want to sort of talk in the abelian setting about a theorem. This is called geometric class field theory that encodes strictly more information than either of these two kind of classical theorems. So this geometric class field theory, it's not something that you usually find in a textbook on Riemann surfaces, at least maybe in Russian, but okay. And I also want to sort of warn, it might not seem like a reasonable generalization of the above theorems. I don't want to say why it implies them, but I hope you can see that there's something of similar nature going on. So to talk about this theorem, I first have to talk about what are called D-modules. So I'm going to start with some kind of scheme. So this is just maybe it's not a curve, it's just defined by some algebraic equations. We write it as spec A, so A will be the polynomial functions on the scheme. And then a D module, I'll make it more explicit in just a moment. So a D module, it's just an A module, like module over this ring, and it also has a compatible action of vector fields on S. So just for example, if S is affine space, so like C to the n, then a D module is just a module over the Weil algebra. So you have n commuting operators, I guess I don't need the laser pointer, the T1 up to Tn, and other commuting operators, these partial derivative operators. And they don't, well, most of the time they mutually commute, but if you pass, for instance, T1 past DT1, they won't commute. The difference between the two will be a copy of the identity. So that's what a D module on affine n space is, and that in some sense controls the entire theory even for other schemes. So D modules are something quite explicit, and kind of explicitly they're the same as quasi-coherent sheaves, so something like vector bundles, but maybe vector bundles where the rank of the fiber is allowed to change or be infinite at different points. So something like quasi-coherent sheaves with a flat connection. And then these D modules glue, so I can talk about them also on non-affine schemes. So like our projective curves, I can talk about D modules or other kind of projective varieties or anything at all. And I can also talk about them on what are called stacks, which I'll talk about in just a moment. So going to refer to vector bundles with connection. All my connections are flat. In other words, a vector bundle with a D module structure, I'm going to call it a de Rham local system. And sometimes I'll just call it a local system. Usually I'll just call it a local system. Some people don't. Okay, most people don't. When you say local system, most of the time, if you've seen this phrase before, it means a locally constant sheaf of vector spaces on like a manifold. And in good situations, those are the same as vector bundles with flat connection. And so for people who work with D modules all the time, it's convenient just to call vector bundles with connection by local systems. So it's a little bit of an abuse of terminology, but the alternatives are worse. So And this phrase de Rham always means kind of, it's a signifier that says I'm now talking about D modules. When I work over the complex numbers and my S is smooth and proper, then these D modules, these de Rham local systems are the same thing as Betty local systems, what I was just saying. So locally constant sheaves of C vector spaces of, I should have said finite ring. And this is locally constant in the analytic topology. So now I want to talk about the Jacobian. Moment. So the Jacobian, kind of a key hallmark of the theory of Riemann surfaces or algebraic curves, is a certain projective variety that parameterizes degree 0 line bundles on X. So the points of the Jacobian are just degree 0 line bundles on X. So over the complex numbers, we can describe the Jacobian explicitly. So it's H1 of X with coefficients in holomorphic structure sheaf, modulo the H1 with coefficients in Z. And this is a copy of C to the G mod Z to the 2G. So it looks like a real torus of dimension 2G with a complex structure. So after choosing a point, there's a certain novel Jacobi map from the curve to this Jacobian. And it induces, so I sort of want to record this for later use, but part of this geometric class field theory story is that you get a map on fundamental groups. It doesn't depend on the choice of point. The fundamental group of this Jacobian, you can just see from this quotient description, is H1 of X with coefficients in Z. It's a vector space mod this. So this vector space is its universal cover. This H1 by Poincare duality, it's the same as, this first cohomology is the same as first homology, which famously is the abelianized fundamental group. And so the fundamental group of X maps to the fundamental group of the Jacobian. Since the fundamental group of the Jacobian is abelian, it factors through this abelianization, and I'm saying that map is actually an isomorphism. So you don't recover the fundamental group of X via this map, you recover its abelianization, aka first homology, aka first cohomology. And I sort of want to highlight for a moment this role of Poincare duality because it'll get referenced again in a few slides. Yeah, but the dual of cohomology is homology, so yeah. Okay, so I'm going to take BunGM to be the stack of all line bundles on X. So well, there's a formula for it here. Let me say something about what stacks are. So the Jacobian, let me remind, the Jacobian was just degree 0 line bundles, and it was a variety. So first of all, what's a stack? So in usual mathematical life, we talk about, like in the very beginning of our mathematical life, we talk about things like numbers, which are extremely rigid objects. And if you have a bunch of numbers like 1, 2, and 3, they form a set. People may have heard. There are some other mathematical objects like vector spaces or line bundles that have automorphisms. And in this case, it's not convenient for sets themselves. It's not convenient in these cases to talk about them as organized into sets. So this is a confusing thing when you learn set theory, is that formally you're supposed to think of sets as forming a set. But they don't, that's not really somehow natural. So what's more natural is to say that they form groupoids, which are kind of generalization of sets. But it's a generalization of sets where you have elements, but the elements also have automorphisms. So an example of a groupoid is like vector spaces with only isomorphisms allowed. So stacks, they're much like something like manifolds or varieties or schemes, whatever your favorite geometric setup is. But in this theory of stacks, groupoids replace sets in the setup. So instead of having kind of a set of points, you have a groupoid of points. Now with that said, SpunGM is going to be the stack of all line bundles. So what does that mean? Well, there's the degree 0 line bundles. There's an extra copy of the integers that has to do with the fact that line bundles can have non-zero degree. And then there's what we call BGM. So this B means that I just say that every point has an automorphism group given by the multiplicative group. So this is kind of a copy of C star, this GM. And so this is saying every line bundle has automorphism group C star. And I'm just remembering that. But it's important to remember this in the theory. If you don't remember it, the theorems aren't true. Okay, so this geometric class field theory, it starts with a construct. Well, the main point in some way is a construction due to Deligne. So what we're going to start with is something I call sigma, which is a rank 1 local system. So that's a line bundle with connection. And attached to this, what Deligne's construction does is define a rank 1 local system, which we call chi sub sigma, on Bun GM. So how does this construction go? So the idea is the following. So suppose you start with some line bundle in Bun GM. I need to tell you the fiber of this chi sigma at that point. So I'm going to start with my line bundle, and I'm going to just write it as O of some divisor. So it's some kind of sum of ni xi's. And then what I'll do is I'll take my sigma, take its fiber at xi, and then tensor that ni many times. So I wrote this in a way that depends on the choice of divisor, but there's a geometric reciprocity law proved by Deligne along the way. It says that actually this was completely independent of the choice of divisor. So, so in other words, it depended only on the line bundle and not on the way I wrote it as O of D. So this is, I say this is a reciprocity law. It's very much in the spirit of the reciprocity laws we were seeing before. It was sort of that there was, like especially that first one, there was some independence of the choice of divisor. So this local system, chi sigma, it has a couple properties that I want to record and also use to subtly introduce terminology. So the first thing is that if I look at the way chi sigma interacts with local modifications, remember I talked about modifying line bundle L to line bundle L prime, then chi sigma plays with these local modifications in a prescribed way. So namely, whenever I have some point in X and some line bundle L in Bun GM, I can do two things. One is I can take the fiber of chi sigma at L of X. So that's like I take L and then I modify it at this point. I just modify it to order 1, let's say. And then, yeah, and so what we say is that that's isomorphic to the following. So it's the fiber of chi at L, but then tensor a correction involving the local system, the fiber of sigma at this point. So this is what we call the Hecke eigenproperty of chi sigma. So Hecke because it has to do with these local modifications, and chi sigma because, or sorry, an eigenproperty because when you take somehow the fiber of chi, it's sort of like you did an operator, this local modification. So think of it as being like a linear transformation. And I sort of looked at the way chi sigma interacts with that operator, and I see that it stays the same, but up to tensoring by a vector space. And that up to tensoring is the eigenpart. So, the idea being that tensoring by a vector space is analogous to multiplying by a number. And the second thing is that this chi sigma is normalized. So that means that its fiber at the trivial bundle is just one-dimensional vector space. So that's obvious from this formula. If you just write O, then you had an empty tensor product, which returns K, according to the deep theory of the empty set. Okay, so now I want to say what geometric class field theory, kind of well, the form I want to call geometric class field theory, I want to say what it says. So informally, what the theorem says is that anytime you have a D module on Bun GM, I call it F, it's canonically a sort of, informally it's a direct integral of all of these chi sigmas indexed by some weights, parametrized by the local system sigma. So informally, we say that this F is an integral over all sigmas of certain vector spaces that are weighting the chi sigmas and integrate against some imaginary measure. That's not really what it says, because you can't, well, it's not what it says. But the idea is that, you know, this F, it's something like an L2 function, and these chi sigmas are kind of like the characters, and this V sigma, it's something like the Fourier mode of your L2 function along the character. So now, more precisely, we have the following theorem, which is due to Mackay, Limon, and Rothstein. And it says that there's a canonical equivalence of categories between the category of quasi-coherent sheaves on Loxus GM, I'll say what that is in a second, and the category of all D modules on this space of GM bundles. And so what is this loxis GM? So before we had the moduli space of line bundles. So here, this is a space whose points are rank 1 local systems. So these line bundles with connection. So it's kind of like before there was this moduli space of line bundles, and now I take some space that fibers over that. That's a line bundle plus a connection. Yeah, and then this category of quasi-coherent sheaves, it was like before when we talked about D modules, I said that you had an action of the algebra A and an action of vector fields. In quasi-co, we don't talk about the action of vector fields. We only talk about the action of the algebra. So this quasi-coherent sheaves is some kind of basic thing in some foundational part of algebraic geometry, whereas, yeah, I didn't put a slide for it because D modules are slightly more exotic. And so just to give a sense for this equivalence, the idea is that if you have a point in this loxis GM, you can put a skyscraper sheaf there. That's what I'm calling this delta sigma. So you take a point, you get a sheaf here. That's going to correspond to some D module on Bun GM, and what it corresponds to is just this chi sigma. And so that's the kind of key property. So we think of this as kind of like integrating over all sigmas. So kind of every sheaf here, you can think of as kind of an integral of skyscraper sheaves at points weighted by vector spaces. And then what we're saying is that, it's some version of this theorem in this case. It says every D module is sort of integral of these chi sigmas, what corresponded to those delta sigmas weighted by vector spaces. And let me just also remark that if you take O, that this maps to the delta D module at the origin here. So the idea is it's like in Fourier theory that somehow on one side you have skyscraper sheaves at kind of characters, and those map to the characters themselves. And on the other hand, you have sort of the constant function 1, and that, which is like a trivial character, and that's mapping to a delta sheaf at the origin. And so philosophically, and also in practice, although again I don't want to spell this out, this encodes all the maybe unramified abelian reciprocity laws that you can possibly think of for curves. They're all sort of hidden here one way or another. So just brief summary of this geometric class field theory. So I want to sort of set up two columns, the geometric side and the spectral side. So there's kind of a stage 1 theorem, which is you can think of as sort of the atomic version of the theorem. And that says that these character sheaves, or normalized eigensheaves, so the things I was writing before, that these are just the same things as rank 1 local systems on the curve. So this is sort of like the character is indexed by the local system. And then there's sort of a stage 2, which I'll call functional analytic, which says that the whole category of D modules on Bun GM is the same as this category of quasi-coherent sheaves on loxis GM. And this can be compared with usual Fourier theory. So in the sort of atomic theory, you might say that if you look at characters of the circle, which are in some sense normalized eigenfunctions for rotations, that these are just indexed by integers. They're all of the form e to the I n theta. Well, 2 pi I and theta. And then there's a sort of souped up version of that story in which you say that L2 on the circle, it's the same as L2 on Z. And so that's why I'm calling it the functional analytic stage. Is it's about the Hilbert spaces instead of just the atomic data of the characters themselves. Maybe a remark is that traditionally in the arithmetic Langlands program, although this is changing slightly but not finished, one sees only kind of atomic statements and not this sort of second order statement. So the existence of this kind of stage 2 statement is really a hallmark of the geometric Langlands program, and it's both its differences with arithmetic Langlands and maybe also what it has to offer for the arithmetic point of view. Coherent sheaves on local systems? Yes. So can I? It's not holonomic D modules. So it's more like locally finitely generated D modules. So like the sheaf of differential operators on Bun GM will correspond to a coherent sheaf. yeah, there's not a good description of holonomic D-modules. But there is a good description of our local systems here, which correspond to skyscraper sheaves over here. And so that's about all you can say. They should have support on all, yes, that's the answer. With the additional thing, UnGM has infinitely many connected components. They should only be allowed to live on finitely many connected components. Yeah, otherwise that's. Other questions? Yeah, right. I mean, it's a reasonable comment to say, which is technically, okay, there's things I'm trying to slide under the rug. One of them is that I like my categories to have infinite direct sums, so I like talking about big objects instead of small objects. And that's because, you know, like, you have, it's because that's what's preserved by normal operations. Like if I want to take a ring and think of it as, or like a K-algebra, and I want to think of it as a vector space, then I typically get an infinite dimensional vector space. And so it's helpful to know not just finite dimensional vector spaces, but infinite dimensional ones. And so that's why I tend to work with quasi-co instead of co. But at the end of the day, you can move back and forth between small objects and big objects. And so in practice, the two pictures are the same, except that big objects have a little more flexibility. Sometimes the things come out, the words come out a little more beautifully in the setting. Like push forwards and pull backs and things like that. So, like if you take global sections of a sheaf on an affine scheme, it'll give you an infinite dimensional vector space. Yeah. And the other thing is that secretly all of my categories are very derived, so if that doesn't mean anything to you, that's fine. In this statement, they are derived, yes. So yeah, this equivalence, it has some version of Fourier-Mukai equivalence built into it, which is not, which requires you to work with derived categories. Again, a lot of the content is about abelian categorical objects, and I'll say something about that later. But along the way, you definitely are working with derived categories. Okay, so now I want to talk a little bit about vector bundles instead of line bundles. So, and the story, it really starts with a 1938 paper by Andre Bay. So it was amazing, actually, for me to look at this paper in preparation for this talk. So in the very beginning of the paper, he says that, he points to many successes in mathematics up to that point, points out that they're really of kind of abelian nature. It says, okay, now what we need to do is start tackling non-abelian generalizations of that theory. And so in this paper, he does this by starting to consider the moduli space of rank n vector bundles on X. He doesn't have like very clear reasons to do this. It's just sort of, he clearly has a strong sense that the theory of curves everywhere, it's about Jacobians, the 19th century theory of theta functions and all of this, it's about Jacobians, and he says, okay, we have to move forward into this non-abelian world. And so one amazing thing from the end of the paper is that he really gives the problem of generalizing sort of a form, not what I call geometric class field theory, but something essentially equivalent, but without D-modules. So for him, it's this division of abelian functions. And he closes this paper by proposing that this sort of non-abelian, the non-abelian extensions of the function field should be related to this Bun GLN. He says it's likely that Artin's reciprocity law, so something abelian, which can be formulated for abelian extensions of a function field and expresses the Poincare duality that we saw before between elements of the homology of a Riemann surface, as a non-abelian analog, which will find its place in the new theory of vector bundles on curves. And so, in other words, he says that in order that the Jacobian controls abelian extensions of a function field, and that maybe there's some similar way that the space of vector bundles controls non-abelian extensions. And this is exactly what happens in the Langlands program. So it took some decades until Bayes' vision came into focus. So it started in the setting of arithmetic and harmonic analysis, And there, Langlands really found the way forward. So in fact, in a 1968 letter to Weil, exactly 30 years later. Then in the 80s and 90s, Drinfeld and Beilinson and Drinfeld proposed counterparts to Langlands' ideas, but in the setting of, that really Weil was considering in his paper, or studying, in the setting of algebraic curves and sheaf theory. So their conjectures extend this geometric class field theory in the form that I explained earlier. And just before I move on to that subject, I have to say a really important role is played by what we now call Langlands duality for reductive groups. And just a comment is that the role of this theory was, you can also see it anticipated by Weil. So what he says is perhaps the reason that the Abelian theory has been so successful lies in duality, and that we should place Pontryagin duality at the center of all of this research. I see I missed some words. But that was the meaning of the comment. And so you can think that in the non-abelian setting, this Langlands duality for reductive groups, it's not the same as Pontryagin duality, but spiritually the same in the abelian case, and it's kind of the right kind of duality for groups. So to tell you about Langlands duality, I have to tell you first about reductive groups. So my reductive groups are always connected and split for people who care about such things. And these are exactly those connected algebraic groups with semi-simple representation theory. Maybe affine, let's say. They include, for example, general linear groups, special orthogonal groups or spin groups, symplectic groups, exceptional groups. There's 5 of them. They have really evocative names, and not a ton more. And so you can take products of these. You can take quotients by finite groups. You can take the multiplicative group. But that's essentially it. So these are in canonical. These connected reductive groups. Just reductive groups are in canonical bijection with connected compact Lie groups. So if connected compact Lie groups are close to your heart, then you should know that they're kind of they're another realization of the same objects in some sense. More fundamentally, these reductive groups, so I said here that there's just sort of a list of all of them, but sometimes it's helpful to forget that there's a list, and remember that what they're fundamentally classified by are what's called root data. So I'll just give a quick sense. So there's some lattice. It's called the weight lattice. It's the lattice. It's just z to the r for some number r, free abelian group, finite rank. So these are going to be the characters of some maximal torus. It has a dual that we call lambda check. So that's also z to the r. Then there's a finite set called delta, and there are embeddings of delta into both lambda and lambda check that satisfy various axioms. Let me just comment. The axioms are completely symmetric in this whole picture. So just a very quick example, if G is GLN, and lambda is lambda check is z to the n, and this delta consists of all vectors, so you take basis vector EI minus EJ, or EJ minus EI, and I shouldn't do 0. So this is I not equal to J. Just to give a quick sense for it. So it follows from this classification that G has what's called a Langlands dual group, G check. That's just that you swap the roles of lambda and lambda check. You stare at these root data, and you see that there's some involution here. You swap the weights in the code, you just do this, and you get some other group by the classification. So the construction of this G check, it's something very kind of idiosyncratic. It's not geometric or group theoretic. So you only really see it once you've classified these reductive groups, or again, classified these compact Lie groups. And its meaning, it's really kind of a priori unclear, and it's best found in the Langlands program. So if you stare at this G check, you read your textbook on Lie algebras or reductive groups or whatever, you see these root data come out, you see that there's this involution, and you just say, what is going on? And the answer, the best place to find it is in the Langlands program. So now I need to talk about G bundles for these groups. So for any group like this G that we were talking about, this maybe reductive group, there's what's called the moduli stack bun G of G bundles on X. So that's like this bun GM we looked at before in the abelian case, but now it's generalized to a reductive group. So for instance, for GLN, a G bundle is just a vector bundle of rank n. For SLN, I also trivialize the top exterior power of the vector bundle. For SON or SPN, then I add a non-degenerate inner product that's either symmetric in the orthogonal case or anti-symmetric in the symplectic case, and also in the orthogonal case, I should say it's SON and not ON. So that's something about having a discriminant one. Or saying that the symplectic volume form is what gave you the trivialization of that top exterior power. Now for the group E8, harder to say what. Okay, similarly, there's a stack called locsys G of, again, Durham G local systems. Let me just give a quick feeling. So for GLN, these are vector bundles with connection, and it's automatically flat because I'm on a curve. For all other classical groups, I add an inner product that's compatible with the connection. Okay, so now I want to start with the statement of the theorem, and I'm going to do this in sort of this stage 2 formulation, this kind of functional analytic thing. So we start with the category of D modules on button G. It's kind of clear how to proceed. I take this category of quasi-coherent sheaves on the stack of local systems, and then you try to prove that the two things are the same. You develop some ideas about how the thing should work, and you realize pretty quickly from this that unfortunately the two are not quite the same. Close, but maybe they're close, but something's off. And so there's a correction that was found by Arinkin and Gaitsgory. So the first step is that you write D modules higher. The next part is you write quasi-co of locsys G check lower. And then there's some other category, which is called indco nilp on locsys G check. So this was defined by Arinkin and Gaitsgory. And what are you supposed to know about it? So the first thing is that it surjects onto this category of quasi-coherent sheaves. So this is a quotient functor at the level of categories. And just to give a quick sense of the feeling about it, I mean, there will be some words later, but let me just say out loud. If you think in terms of small objects, so there's, you were asking before about coherent sheaves on the space of local systems. But in fact, when you're on a variety, there's kind of two notions of small objects if you work with derived categories. One are coherent sheaves, or maybe bounded complexes of coherent sheaves. But there's a smaller setting, which are bounded complexes of vector bundles, or said better, perfect complexes. And for smooth schemes, the two notions are completely the same. This is kind of what you learn in Matsumura's commutative algebra. It's this Serre theorem or Hilbert-Syzygy theorem or various things in this direction tell you that in the smooth world, these two notions are the same. But in the singular world, they're different. And so, so this quasi-co, if you're very careful about things like Thomason and Tribot were, you realize that it's connected to perfect complexes at the small object level, not to coherent complexes. So this quasi-co, it's sort of more synonymous with perfect complexes, these bounded complexes of vector bundles. So in other words, objects like sort of coherent sheaves that have bounded resolutions, bounded projective resolutions. This indco, it has to do with coherent complexes instead. It's the same sort of relation. And this co-nilp is something that lies in between. So it's something somewhat specific to this locsys G check, but in a general geometric framework. Yeah, that's the flavor of it. So the way that sort of perfect complexes you can enlarge to coherent complexes, Arinkin and Gaitsgory said don't enlarge that far, but just to here. It's coherent sheaves with what's called nilpotent singular support. So so coherent sheaves with nilpotent singular support, which is some kind of notion. Said, I mean, there's a different point of view just for the sake of completeness. So whenever I have a parabolic, I get some correspondence like this. So just saying for people who know this stuff. And this map is proper. And so what I'm going to do is I'm going to take all parabolics, and I'm going to take all complexes of the following form. So I'm going to take a perfect complex on this locus M check. So this is a parabolic which lives inside of my GLN, and its quotient is like this. So this is P or P check, this is M check, and this is G check. It's the Levy quotient here. Yeah. So I take a parabolic and I take its Levy quotient, and there's a certain object. So I take a perfect complex here in this Levy. I pull it back. I get another perfect complex, and then in particular it's coherent. And then I push it forward along this proper map. And now it has no reason to stay perfect anymore. It'll just turn into some coherent complex. But I take all of these over all levies, and that's actually a description of what this is. So those are the certain coherent complexes that I take. The NOPE is a different point of view on it. So yeah, what I said is it's a theorem that, yeah, the theorem of Arinkin and Gaitsgory. It's always smooth, yeah, always smooth, always projective. Yeah, I can tell you more about it after. And then, so kind of on this side, I made something bigger, but I can do something parallel, which is I can make this smaller. And this is what we call the category of tempered D-modules, which plays an important role in the subject and is harder to define. And then what the theorem says is that there are equivalences. We call LG for Langlands functor. There's an equivalence between D modules on bun G and this larger category, or an equivalence between this weird, but the larger category is not, the formula is longer. It takes, what, 10 symbols instead of 4 symbols. And over here, there's this also smaller object, but also a little bit weird. And the statement is that the guys on top are equivalent and the guys on bottom are equivalent. So that's what our theorem is saying. So there are these differences I'm highlighting above. So sort of this difference and this difference, both due to Arinkin Gaitsgory. And these are related, like this NOPE says, to G-check local systems that have nilpotent endomorphisms. So like that's what I would really say for a vector bundle with connection. It's kind of, you can talk about flat, like endomorphisms as a vector bundle with connection, and you can talk about it being nilpotent or not. And if you have a local system that has a nilpotent endomorphism, it's causing you the sorts of headaches that are on this slide. And for general G, that just means a flat section of its adjoint for people who know what that means. So in particular, none of these issues arise over the locus of irreducible local systems. If you have a vector bundle with connection that's irreducible, then it's never going to have a nilpotent endomorphism at 0. So on the right-hand side, like I was saying, the differences that occur involve coherent versus perfect complexes. This notion of temperedness on the left-hand side, it's really something fundamental in the subject, but it uses structures that are very particular to this automorphic theory. We call it. Automorphic means dealing with D modules on bun G. Well, that's what it means in the geometric setting. So it's something very idiosyncratic and not easy to explain in non-technical talk. But now, okay, so that was the statement of the theorem in the stage 2 formulation, the sort of functional analytic version. And now I want to say what we know about it in the stage 1 formulation. So more kind of in categorical terms. So the first thing is that for every local system, there exists a unique, so normalized like before, but now I'm supposed to put the word Whittaker in front. Hecke eigensheaf. So I'll call F sigma. And then it's going to be in this tempered category. That ensures the uniqueness. And so this temperedness, again, you can ignore, for instance, if sigma is irreducible. Let me suppose for simplicity that sigma is irreducible. And this F sigma, it's actually perverse. It's in the heart of the T structure, or whatever you want to say. It's semi-simple. its simple factors are indexed by irreducible representations of the automorphism group of sigma. So for most people, so these, if you think in terms of representations of pi1, this is like the group of all elements that commutes with the image of your fundamental group representation. For GLN, that's just the center of G check. But in general, it's an extension of a finite group by the center for a general reductive group. So there's something a little weird that happens. Each of these simple factors occurs with multiplicity of the dimension of the representation. I just want to highlight to say that this is similar to phenomena that people see in the world of L packets in the arithmetic theory. And then for the sigma, any sigma without nilpotent endomorphisms, in fact, well, the characteristic cycle of this F sigma is going to just exactly equal the global nilpotent cone, which is something. And there's a slight technical hypothesis here, although. So it's what's called the characteristic cycle of the sheaf. So, so if you have, well, it's not written because I'm going to move. It's not required. So there's SS, there's the singular support. So SS, it actually has an enhancement where all of the irreducible components have numbers, integers attached to them. Does that make sense? So this is called the characteristic cycle. So for instance, if you, again, as a comment for people, but so like if you have like a vector bundle with connection, its singular support is like the 0 section inside of here. And you can, but if you have this vector bundle with connection, you can put an extra integer here, which is the rank of the vector bundle. That's called the characteristic cycle. And in general, in fact, you could have other singular support, but you'll actually have integers at each component. They compute orders of some vanishing cycles. They do various things, but yeah, that's called the characteristic cycle. So in particular, the singular support equals the nilpotent cone, but more than that, we know things like the rank of, this F sigma. It's a de Rham local system generically, and we know the rank, for instance, of that in this calculation. And it gives us extra numerical data. That's somehow these generalizations of the rank of the vector bundle with connection. Okay, so I just want to give a kind of brief overview of a little bit of how things proceed. This is a little bit more technical. Yeah, but maybe one thing I just want to highlight maybe before going on is like before I talked about these chi sigmas in the case of GM, and they were something quite explicit. I essentially wrote down a formula for what they were, and and this formula, again, was quite explicit. This F sigma, it's a much less explicit object. So I'm putting information, for instance, about its characteristic cycle because, for me, that's a kind of question that makes sense about, well, there's a nice statement for what the characteristic cycle is. And I like the statement because it tells me something about what this F sigma looks like. But in general, I find this F sigma still to be a pretty inexplicit object. I know how to prove various things about it, but I just sort of want to be upfront about that fact. Yes. So that it is semi-simple. So you can do that intermediate extension process here. The problem is you take some big open inside of bun G where it's the local system, and then you want to like maybe describe that local system as depending on the sigma, and that's not an easy task. Like it's one of these things where like the meaning of explicit in mathematics is a little bit opposed, but like having some kind of explicit description of that F sigma would be very great. Yeah, so for GLN there is some kind of explicit description, and actually in some sense what I'm writing on this next slide, it's just a naive generalization of that explicit description, but less explicit for G somehow. I don't know. Okay, so this nilpotent cone. So like in this case, whoops. Okay, this nilpotent cone, it's a scheme. And so schemes can be non-reduced, yeah? And so they have a notion of multiplicity. So if it were a fat point, the multiplicity is the order of it's the dimension. And, yeah, okay. And so this, yeah, the nilpotent cone, it's defined by explicit equations, and it is not at all a reduced thing. And so the numbers you see here, what that means that it's the global nilpotent cone is that the integers here are the multiplicities of the irreducible components of the nilpotent cone. That was your, yeah. Yeah, exactly. Yeah, it's yeah, exactly. The actual structure sheaf of the coherent of the global nilpotent cone in the Chow group gives you this characteristic cycle. Okay, so I want to give a brief overview of how things proceed, and brief, really brief. Okay, so the first thing is that there's a theorem of Drinfeld and Gaitsgory, which said that. So this quasi-coherent sheaves, it's what's called a monoidal category. You can tensor sheaves together. So that gives you a sort of binary operation. And the structure sheaf is the unit. And it makes sense to talk about a monoidal category acting on some other category. And what Drinfeld and Gaitsgory showed is that using geometric Satake and many other ideas, but geometric Satake, which is encoded in these Hecke symmetries, somehow this idea of moving from one bundle to another bundle by local modifications at points, that this actually induces an action of quasi-coh of log-cis G-check on the category of D modules. This is a really important theorem in the subject. Really should, I'm summarizing it in one sentence, and that might not totally give a feeling for what's happening, but this is what they prove. So the next thing is that you can take a Borel, so this is kind of like this, well, you take a Borel, so these are like upper triangular matrices in the case of GLN with radical n, so this would be like the unipotent matrices. And then you can take a maximal torus, which is the quotient of the Borel by n. So it's like this picture, but for GL2, like in the case of GL2. In this case, we define a certain twisted version of bun n, which I write as bun n omega. And these are sort of all B bundles whose induced T bundle is not trivial, but is what's called row check of omega 1. So that's a certain T bundle. Yeah. So then there's a certain kind of Whittaker style map, call it. So it goes from this bun n omega, and it's roughly bun n, see where the omega comes, to I take the product over all of the, well, product from I equals 1 to the rank of the group, copies of bun GA of omega. So these are like GA bundles. GA bundles would be classified by a class in H1 of X with coefficients in O, but because of this omega business, it's classified by a class not in the structure sheaf, but in omega 1. And then I can apply Serre duality to say that's just A1, but R many times. And then I can sum my coordinates to get down to A1. So this is a canonical character of this bun n with the twist going down to A1, sort of additive character, you should think. Then I take what's called the exponential D module. So that's just O of A1 with a connection given by the exponential differential equation, D minus dt. In other words, it sends like a function little f to like f prime minus f, all of that times dt. So it's the thing where if you took its kernel, you would get the exponential function, except that's not a polynomial, which is why this is non-trivial. So I take this exponential local system, I pull it back to this bun n omega, and then I take some kind of push forward down to bun g. And this is giving something which is called the Poincare sheaf, and which I call Poink, the little shriek, and it's some D module on bun G. So it's some explicit construction. This is an analog of the Dirac delta in abelian Fourier theory. So in abelian Fourier theory, the key role is that the key point is that like delta functions are exchanged with characters. And here this is the delta at the origin, so to say. So and that's literally what we get in the case of GM multiplicative group. Then this is trivial. I did nothing, and then I just took some push forward to bun G along the trivial bundle. So I really was getting some kind of Dirac delta function. in that setting, or delta D module in that setting. So these are kind of the two main ingredients for setting up the theory. So I have to first have the spectral action, and I second need this certain Poincare sheaf. And once I've done this, which is like in Fourier theory somehow having like symmetries, like there's the rotational symmetries that briefly were on the board for the circle. So those are the symmetries of L2 of S1. Here we have these Hecke symmetries, which are encoded in this action of quasi-colocus G check. And then second, I need sort of this Dirac delta analog. And this, smart people teach us, should be given along the following lines. This is a different notion of Poincare sheaf. Yeah. So that's a fair point, and it's a different usage actually. Yeah. This here it's inspired by the construction of Poincare series in the theory of automorphic forms. So it's a certain construction of automorphic forms, quite analogous to this. Like there you would sum and some exponentials, and here sort of some exponential sheaf. Okay, so now there's a brief overview. So again, we'll just go through sort of the slides from before. From here to here. So yeah, it's just it's like if you okay, great, yeah. Like bundles are classified by H1. Okay, so brief overview is that, okay, I have this world of D modules on bun G and this world of quasi-coherent sheaves on Lopez's G check. And we're going to enhance them as the slides go on, but my goal for now is to connect the two to start. These are the two easiest objects. The first thing is I can just take maps out of this Poincare sheaf, and that gives me a map to just vector spaces. Now the next thing I can do is I can take some kind of inner Hom, some smarter object against the Poincare sheaf, and that's going to map me actually to quasi-coherent sheaves. So here, when I say Hom, it's like, well, my category is enriched over vector spaces. Homs in here are vector spaces in this world of D modules. But once you have that spectral action, you can actually, just for free from category theory point of view, you can actually just talk about inner Homs, which will be quasi-coherent sheaves here. So that's what I've written this complicated way. It's just the inner Hom thing instead. It recovers the previous functor by taking global sections. So next, there's a claim, which is just some kind of stuff we know about the Poincare sheaf. That says actually that functor factors through this quotient, this tempered D modules, which I didn't define, but say the Poincare sheaf has this property. It plays well. It is tempered in some sense. So Hom out of it factors through this quotient. That's some, have to use some bit of knowledge here. So now I want to get up to this indco instead. So I've constructed something. I've constructed this tempered Langlands functor, but now I want to get actually to the Langlands functor itself. And the statement is that there's going to be a unique lift, which is exact up to shift. So here, the Langlands functor, it's not supposed to be oops, actually I wrote it. I wrote it incorrectly on the slide actually. There is space for a shift upstairs because the categories involved are pretty complicated. I can't believe I screwed it up. The correct statement is going to be that it sends compact objects here to objects that are bounded below here. I should correct this. So it's wrong for subtle reasons. But the point is, so spiritually what's happening is that by sort of just looking at the T structures, like looking at the abelian categories, and looking at things like cohomological amplitude, you see that there's a unique functor that's compatible with this diagram, subject to some conditions involving those T structures. And the key point here, let me say, is that one of the key ideas is this int code is something exotic. And maybe I should have said before, the difference between coherent sheaves and perfect complexes, coherent complexes and perfect complexes, is familiar to people who think about these things. But this int code is something newer in the subject. And one of the reasons is that these two categories are very close to each other, actually, on these big objects. So you can think that this is, it's not an equivalence for good reasons, but it's close to being an equivalence. And this idea that it's close to being an equivalence is what gives you this lift. I'm out of time. Ooh, okay. Let's discuss in just a moment. Then there's the hard part, which is showing that this is an equivalence. And very briefly, this is done by using many old ideas in geometric Langlands. It uses some new techniques, and it also uses a bunch of tricks. So that's the end.
Let's have a quick question. Any questions? Okay, actually I have a question. How did you use this first ingredient, this spectral action?
So I used the spectral action to get, oops, yeah. I used the spectral action here. So I don't know spectral action here, spectral action here. So in order to get this diagonal functor, using this inner Homs. So in other words, I need this to act on this in order for this functor to make sense.
All right, maybe I will ask you later.
Okay, yep.
Yeah. Let's thank Professor Raskin again for his wonderful talk. Okay, there will be no break. We will have our next talk.